Hello everyone and welcome in this new recording. Today we will be talking about how you can generate this kind of Voronoi diagram. There are a few steps to get to this result, but you will see that in the end it's really not that complicated. For my part, I'm planning to use this effect to build some kind of background for some of the recordings that I will make from now on. And in fact, I'm probably going to start using this right now. So are you ready? Let's get started. Alright, so the first thing we need to do to build this Voronoi diagram is to consider a grid of points. You actually need to generate some random points. Or maybe you want them to be not that random. But yeah, let's just say you need a grid because it's easier this way. In this case, I'm using a 10 by 10 square grid, but it doesn't have to be square. It could be rectangular, and it doesn't have to be 10 by 10 of course. It could be much less or much more elements on your grid. Once you have this grid, you start with considering the points implicitly defined on that grid. And this will serve as your initial set of random points to build the Voronoi diagram. Except that currently they are not really random. So what you can do next is to add some kind of random displacement for each of those points. So for instance, here is an example of such a displacement effect. You do that for every single point, and that gives you a set of random points like this one. Now, the displacement here is relatively small, which is pretty useful to keep the points in the vicinity of the origin location where they were created, and thus avoid too much randomness. But if needed, you could in fact increase the displacement. Here is, for instance, another example with a max displacement value of 1 unit. You see that the points are moving significantly further, and the end result is noticeably more random. And here you go with an even higher displacement that gives you more chaos. But sometimes when you do that, you get points that are very close one to another, so you may want to stick to a regular, not that large displacement value like the one we use initially. In any case, in the end, you get this type of result. So that's a list of random points that you will use for the generation of your Voronoi diagram. And of course, at this point, you can imagine that this could be changed to another list so you could produce different set of random points, just by changing your initial random seed, for instance. Or you could consider changing the size of the grid itself, as mentioned initially, to get maybe less points or much more points. Now in my code, to generate this kind of grid, I have created a dedicated Voronoi Diagram class. This class is what I am using to create those initial set of random points given the desired grid width and height values, and internally we will store a vector of points like this. The function itself is pretty simple. You start with preparing a container for your list of points, simply resizing your vector here. Then you figure out what is the offset that you want to actually generate a grid of points centered on the origin of your coordinate system, and you iterate on each row and column of the grid. For each point, you start from the default grid location, then you apply the common offset, and finally that's also the step where you will add the displacement, both in the x and y directions, before you move to the next point. And that's it, guys. That's really all you need to generate your set of initial random points. Once you have your input points ready, the next step is to perform the Delaunay triangulation of those points, which will give you this kind of result, for instance. Naturally, if you change the list of points, you get different triangulation results. Now, the question is, how can you perform this triangulation operation? That step is something that I'm not really considering as part of what we should implement ourselves here, because as far as I understand, it can be a bit tricky to do it right. So instead, we will simply use an existing library to perform this operation. In fact, I found at least 3 different libraries that you can use to perform the Delaunay triangulation. The first of them is this one. It seems pretty convenient and you can do a lot of things with this library, but I didn't actually test this one myself. The second one would be the Delaunay CPP project. This one is inspired from the JavaScript implementation from Mapbox, and it should also be pretty efficient and very fast, as you can see in the benchmarks, but that's still not the one I'm using myself. The one I decided to test is this one, the Delaunay library. This seemed a reasonable choice because it is still open source and it's apparently the most recent of those 3 libraries, so I would assume that it's using the latest available algorithm, and the README mentioned using the Newton Apple wrapper algorithm, apparently, something like that. And yeah, you can do pretty nice things also with this one. And there is even a nice minimal example on how you should use this library to construct a Delaunay triangulation. I actually started from this code here to generate my own version of it. And on top of that, the repository also provides some benchmarks comparing the Delaunay library with the other libraries. The Delaunay CPP library is also pretty fast most of the time, but you also have some cases where the Delaunay CPP library would go a bit sideways compared to Delaunay. So that's another reason why I thought that Delaunay would probably be my best option for the moment. I have thus extended my Voronoi Diagram class, providing an additional triangulate function. And now you can also retrieve the list of triangles once they are generated. The triangle is a simple structure which contains 3 indices, and those indices are of course mapping directly into our previously mentioned list of points. And in the class we added storage for the list of triangles, of course. The triangulate function, as I mentioned, is using the Delaunay library. We start with checking if we have some points, because if you have no points, then of course there is nothing to triangulate. Then you create this interface and you call this triangulate method. You need to provide the number of points and a pointer to your x and y coordinates. And according to the documentation for this function, if you don't specify the y coordinate, it will be assumed that this coordinate can be read just after the location of the corresponding x coordinate for every point, which is our case here. And then you have the stride value, which is the size of a simple 2D vector for me. Once this is done, you need to check if we have some vertices or not. If not, it means that the triangulation failed, and otherwise you can continue by retrieving the number of polygons, which is really the number of triangles in this case. And at this point, I'm going to prepare my container on my side to store the triangles. Next, you simply iterate on the Delaunay simplex that you get from the Delaunay library. Each simplex will contain the indices that you want for the different vertices used to construct a specific triangle. And you just move to the next one until this loop is completed. Once you have all the triangles constructed like that with the triangulation process, the next step for you will be to compute the center of the circumcircle for every triangle. In case you don't know what this circumcenter is, it's pretty easy to understand. For every triangle, you can in fact construct a circle that passes through all 3 vertices. So this would be an example of such a circle. And this will be the center for the circle. You have different options to construct the circle and get the center coordinates, but the easiest one that I found myself is this one, the Cartesian coordinates construction. The Cartesian coordinates of the center will be given by those 2 formulas here, with this definition for the variable d. On my side, I just slightly updated the triangle structure. Now also adding the circumcenter coordinates directly in the structure. And when performing the triangulation, for every triangle that I would retrieve, I'm now also computing the circumcenter given the indices for the points that are used for that triangle. So here is the compute circumcenter function, which will use those 3 points to perform the computation of the center. You see that we start with the computation of the value of the d variable, and from there we need to compute the ux and uy variables, which are the coordinates for your center. So these are the formulas that you will find on Wikipedia, but in fact you could generalize this to handle those two components together if you just perform the computation on the vectors like this, and at the end just add a simple clockwise rotation of 90 degrees, which will provide you the inversion that we have here on the x and y dimensions. And that's all you need to get your circumcenter. So now we can display all those centers for the triangles, here in yellow for instance. Again, different constructions give you different centers. Okay, so we are almost there. The remaining step is that for every point in your original list of random points, you need to consider all the triangles that are using this point. And from all those triangles, you retrieve their circumcenter. And finally, all we need to do is to link all the circumcenters together, which will give you one Voronoi cell around that specific random point. So if we do this for all our random points, it will produce this kind of result. So here we are. This is officially our first generated Voronoi diagram. Yet you will probably notice that we still have some points here outside of the diagram. And that's simply because at the border of the Delaunay triangulation, some points will not be completely encapsulated in a Voronoi cell, since you need at least 3 triangles using that point to be able to display a cell. But in some cases you will get only 1 or 2 triangles using a given point. So that's why it can be handy to add some points to your initial list outside of the area that you really want to triangulate. For instance, here is what I will get if I had 4 additional points distributed on a circle reasonably far away from the main grid location. In this case, we will be able to generate a valid cell for all our points on the grid itself. And again, at this point, you can consider generating different sets of input points. You can decrease the grid size or increase it. In all cases, you will still be able to generate the Voronoi diagram the same way. Now, on the code side, to be able to generate those cells, what I need to do first is to prepare a container here. For every input point, I will need to store the list of circumcenters that are immediately around it. So we need a vector of center points. Next, when I perform the triangulation operation, I now also add the just computed center point here to the list of center points to be considered for each of the points that are used to construct the current triangle. So we use the indices 0, 1, and 2 here. The add cell point function is pretty simple. You just retrieve the list and you append the point. Initially, I was trying to order the points at this step, but this actually didn't really work. What I'm doing instead now is that I first iterate on all the triangles, populating the list of center points for every point in the process, and only after that I will go through each of those cells and I will sort the different circumcenters given this arctan computation to ensure that all the circumcenters are ordered in a counterclockwise fashion around our current point of interest. This is needed in my current rendering mechanism, as this ordering is required to display the Voronoi cell polygons properly. So now that we have our first Voronoi diagram generated properly, the final step that I would like to cover is on how we can animate the random points that we use to generate the diagram. If you start moving those points on each frame, the idea then would be to recompute the triangles and also then recompute the circumcenter for every triangle, and that will allow you to recompute your Voronoi cells on each cycle. And here is the result that this will produce. You see that the points are moving and the cells are updated dynamically. The nice thing with this animation mechanism is that we'll still have some control on how the points will move, because I am also providing a small control interface here, and from there we can set how much the points will be attracted, for instance by their respective original location on the grid. If you increase this value, you will see that it's going to control the movement of the points and actually move them back to their original grid position. If you reduce this other parameter, it's going to be even more visible. But we can do something different here, which is to increase the attraction of the point towards the current center of its cell. So that's what you would call relaxation of the Voronoi diagram, in fact. Or at least we have some kind of approximation of it here. But first, if we put the origin point attraction to almost 0, then the points will basically move randomly, which is also a behavior that might be interesting in some cases. And now if we increase the cell attraction, then you see that the points start to get distributed a bit more evenly and produce cells that are slowly becoming more self-similar, most of the time at least. Yet, we see that this also comes with a tendency to attract the points more and more towards the outside of the original grid location. To be honest, I'm not quite sure why. I should probably try to display the full diagram, including the border points, to get a better idea of what's happening, but that will be for another time. So now we have a working animation mechanism, and I think this is basically it concerning the visual demonstration part. The only remaining step for us is to have a quick look at the code to discuss how we're building this animation process. So let's see that. To provide the support for the animation of the diagram, I had to update the structure that I use for the point definition. Instead of simply providing the position of the point, I'm now also providing the center location, which is what I called the origin previously. So that's the initial position of the point, and you want maybe to attract the point towards this initial position in some cases, as just demonstrated. And we also have a speed value, which gives you the speed intensity. That part is randomized, but it's not going to be changed dynamically. We also have then an angle, which is telling you what is the orientation for the speed vector of this point. And this orientation will be changed progressively. Now, in the create point function, we proceed slightly differently. We're still going to generate a random initial position, and this initial position is what we call the origin, or the center, as we have it here. And then we also provide a random speed. This will be limited because I didn't want to see the points moving too fast. And finally, we generate a random angle, which gives you the initial direction for the speed used to describe the movement of this specific point. Next, we also have this new animate function in the Voronoi diagram. And here is the code for the animation process. We're of course iterating through all the points, and for each point, that's the part where we figure out what is the cell center. For that, we retrieve all the circumcenters that are used to define the Voronoi cell for this point, and if we perform some kind of mean value computation on all those circumcenters, that should give us an acceptable approximation for the cell center. And we use an attraction force towards this center of the cell, applying a factor here to give us control on the intensity of this attraction. Similarly, we have another attraction force towards the origin location for the current point, and we apply a different factor here. Finally, that's the part where we have some kind of Brownian motion at play, as we had a randomized small increment to the direction angle. So the direction will only change progressively. From that, we can generate our speed vector, and the position will be updated by adding the speed multiplied by the elapsed time. I mean the elapsed time since the last frame, of course. And we're also taking both attraction force from above into consideration in this process. Alright, so this is it, guys. I hope you found this recording interesting and you learned something. And well, it's only a simple introduction, I guess, on this Voronoi diagram generation concept. There would be probably much more to say on this topic. There is in fact still a lot to do on my side, because in this simple example, the performances are not very good. But I'm going to work on this a bit further, and I'm sure there will be ways to optimize the results. Anyway, as I said, I'm going to use this as a basic background for my tutorial YouTube recordings already, because I really like this effect. And in any case, if you have any question, as usual, just let me know in the comments and I'll do my best to help if I can. And otherwise, I'll see you in the next recording. So have a nice day and see you next time. Bye bye!